दिखा तो रहा है।
We'll wait for a few minutes for others to join. Okay, let's start. So welcome everyone to week 2 tutorial for the course IC engine and gas turbine. So am I audible to everyone? Can anyone of you confirm?
Audible, sir.
Okay, thank you. So in the previous tutorial, we have finished up with the what is the petrol engine, how the cycle works. We covered the different component and geometry of the IC engine. Then towards the last, we saw about the volume flow rate and the square ratio and over square ratio concept. So today we will start with the Otto cycle. Okay, so as one of you suggested in previous tutorial when we will start. So yeah, so we are starting today the Otto cycle. Let me share my screen. And I hope everyone is like regular to their assignments, as well as they might have watched the lecture videos by the professor, or those who have missed or want to repeat any of the lecture of the last week tutorial lecture. So I hope you might have gone through it. I have already shared my YouTube channel on which the video was already uploaded. after the lecture itself, as well as the notes are also provided in the video description. Okay. All right. So let me share. I think screen is still not shared. Start broadcast. I hope my screen is visible now, right? Okay. So let us start. Let me switch on the camera. Okay. All right. So I hope my screen is visible now. Can anyone of you confirm? Okay. And whatever I'm writing on the screen is also visible. So we'll start with auto cycle. If at any point of time you feel you want to ask anything, you can stop me and ask, as well as at any point of time, if my audio goes off or my video goes off or my screen shared goes off, please immediately point me out. Okay. Don't wait to uh, for anything. If you immediately find it out, please point me. Okay. So that I can immediately switch the network and fix the issue. Okay, so let us start the cycle, the auto cycle. So the name, the auto cycle was given based on scientist Nicholas Otto because they made the cycle. And as we know, the petrol engine, it is for a petrol engine cycle, basically to describe the process of the petrol engine cycle. So we have 4 strokes in the engine, as we discussed in a previous tutorial. One was suction stroke, then compression stroke, then power stroke, and finally was the exhaust stroke. Okay. So let us start uh, describing it in a graphical as well as a mathematical form to find out the efficiencies. Okay, so there is a difference from your thermodynamics. It is not a Carnot cycle. If you all remember that the Carnot cycle, their heat addition and heat rejection are occurring at the different temperatures. Okay, and it is an external, sorry, in heat addition and heat rejection are occurring in the Otto cycle at different temperature, whereas, and it is also an external reversible cycle, but Carnot is externally as well as internally reversible cycle. Okay, that's why its efficiency is maximum, but in practical scenarios efficiency is not maximum of any engine. Okay, so I hope, yeah. All right, so let us start. So we will make few assumptions while dealing with the auto cycle which were taken. So assumptions are as follows. I hope my screen is visible. Can anyone of you please confirm me and my audio also? Anyone of you can unmute yourself and confirm?
Yes, sir, it is visible.
Okay, great. So we are using air, which is the working fluid here. Okay, first thing is that. Second scenario is that air is taken as a perfect gas. Okay, so that we can apply the equation of state, that is PV is equal to MRT. Okay, and we assume that the specific heat at constant pressure and volume Cp and Cv, as well as the gamma, is also constant. That is your adiabatic index. Okay, let me write. Air is the only working fluid. This is the only. Today we will do few numericals as well. Okay, so that you get the idea of how to solve these uh, efficiencies, the cycle from the petrol cycle. Okay, so that no, so air is taken as the working fluid, and as well as air is taken as perfect gas. So that we can apply PV is equal to MRT. Okay, and Cp, comma Cv or index all will be constant. Okay, all will be constant. Okay, so let me draw the, so whenever we are describing a cycle, okay, we will have pressure and volume plot so that we can get the work done out of it, and temperature and entropy plots so that we can get the net heat from the system. Okay, these are the only energies, heat and work, which we basically wants. The difference of this will give us the internal energy. Okay, so let us first of all plot pressure volume. Use this. Okay, pressure volume plot. Okay, so what was our first process in the cycle? The first process was after suction, the compression starts happening. Okay, so first of all, the compression happens. Okay, of the air film, air fuel mixture. So, and this is an isentropic compression. Okay, that is adiabatic reversible. Adiabatic reversible is an isentropic process. Isentropic means the entropy of the system remain constant. All these are the part of the assumptions. The one of the basic cycles of a petrol engine, we are starting with the Otto cycle. Okay, that's why we will come with the real cycles as well in the later part of the course. Don't worry about that. But first we have to develop the basic understanding that how the cycle basically works. Okay, so the first one is the compression process. So when we are compressing, so we have assumed that the suction has already happened, and when we are compressing, then eventually the pressure will rise and the volume will decrease. Okay, the volume will decrease. From mathematically also, if the pressure rise in this equation, then the volume will automatically will decrease to maintain the value of the right hand side. Okay, so pressure increases during the compression, the volume also increases or decreases. Okay, decreases, and it's an isentropic compression at constant entropy. So I say that, let us suppose this was the state 1, this is state 2. The compression has happened from position 1 to 2, from position 1 to 2. Okay, so this was, if your cylinder looks like this, suppose, let me draw a cylinder here. This is your cylinder, and this is your piston inside the cylinder at TDC. So this situation is your TDC. This situation is your TDC, and this situation is your BDC. So from BDC to TDC, the compression has happened. Okay, so this was initially your clearance volume. We have discussed what is clearance volume, the volume between the piston head and the TDC, and this is your swept volume, Vs. Okay, Vs. So this is your swept volume. So first process is isentropic compression has happened. Okay, what was the next process? The next process was an heat addition at constant volume. Okay, so if the volume is remaining constant, then heat is added, and eventually the when the heat is added, eventually the pressure is going to rise. Okay, has anyone tried to join? Okay, when the heat is added, pressure rises at constant volume and heat is added. So the next part will be heat addition. The volume is constant. If you see, I have maintained the volume constant. This is your step 2 to 3 process. Okay, heat is added as a constant volume. So that means I will use a red color. Heat addition at constant volume. This process was PV raised to the power of gamma is equal to constant because it's an isentropic compression constant, adiabatic reversible. Okay, this is a compression. Okay, compression process. 2 to 3 was a heat addition process. Then 3 to 4, what happens? Expansion happens. That is your exhaust. Oh, sorry, power stroke happens. Okay, power stroke happens. So the next process will be, again, it will be a isentropic expansion. First 1 to 2 was isentropic compression. 2 to 3 was heat addition at the constant volume. 3 to 4 is isentropic expansion. Okay, that is your power stroke. So slope will be same eventually. So slope, both of these lines are parallel to each other. You have to make like that, because slope of a will be remaining same, because both are the isentropic processes. So this will be your fourth point. Okay, and final was from 4 to 1, your exhaust happens where the heat is rejected out from the system. So 4 to 1 is a heat rejection at a constant volume. Okay, so this is heat rejection at constant volume. That was heat addition at constant volume, and this is isentropic expansion. PV raised to the power gamma is equal to constant again. Okay, and this is isentropic expansion. And we know that area under the pressure volume graph, that is work done. P into dV is your work done. PdV is your work done for a closed system, not for an open system. This is a closed system scenario. So area under this whole graph will be your net work done. So this depicts your PdV is nothing but your work done. So this is work net work. Okay. If area is directly given to you, that means you are getting the net work. That is why we plot pressure volume plot. Pressure volume plot. Okay. What will be the and eventually the temperature entropy plot will be our second scenario, from where we get the net heat interaction. So let us draw temperature. Use this color. So this is your temperature entropy axis. Okay, temperature entropy axis. So 1 to 2 was a isentropic compression. Isentropic, that means entropy, that is x-axis is maintained constant. Isentropic compression, when you are doing compression, pressure increases, temperature increases. So your 1 to 2 will be like this. Isentropic compression, entropy is maintained constant from 1 to 2, and temperature has been increased. Temperature has been increased. Okay, here also arrows are necessary, that how your cycle goes. Okay, if you don't put arrow and directly make this rectangle box, something like that, you are going to get 0 in your, because we don't know it's what is the direction of the cycle. It's a work producing or work absorbing device. We don't know that. But uh, yeah, so we are producing a work that is from low grade form of energy to high grade form of energy, converting heat to work. So 1 to 2 is your isentropic compression process. Next 2 to 3 is your heat addition at constant volume. So whenever you are doing heat addition at constant volume, eventually temperature is going to rise when you're providing some heat to the system. But how will the slope will be? Let us first draw the slope, the process 2 to 3. Okay, so temperature has increased. Whenever you are adding heat into a system, entropy is also going to increase eventually. Okay, so 2 to 3, but we don't know what will be the slope. So let us identify. Oh, why is this issue coming? Sign in again. Okay, I hope, yeah, this works. All right. Is my screen visible to everyone still?
Yes, sir.
Oh, okay.
Visible.
So 1 to 2 was a isentropic. Already I've written the process name, so I'll not write on the TS plot again. So 1 to 2 is a isentropic compression. 2 to 3 is a heat addition at constant volume. Okay. Then 3 to 4 is your isentropic expansion. Okay, isentropic expansion. Then that means again entropy is remain constant. And whenever you are doing expansion, your temperature is going to drop. Okay, expansion means temperature is going to drop. 3 to 4. Okay, and final was heat rejection at constant volume. So whenever you are taking heat out of the system, that means your entropy is going to decrease. Okay, so 4 to 1 is your, and temperature is also going to decrease because you are taking heat out of the system. So 4 to 1 is your isentropic, oh sorry, heat rejection at constant volume. Okay, now the question arises, what will be the slope? I know that. So if you don't know what will be the slope of this TS plot, so what we can do, we know that dq is equal to du. Net heat interaction is net internal energy. Okay, we know that. So it is a function of cv dt. And what is dq? That is tds from entropy equation from thermodynamics. So you get the slope of dt by ds, that is slope of ts graph. If you rearrange, it will be t over cv. T over cv. So both are constant volume process. Either it is from 2 to 3 or 4 to 1. So your slope will be t by cv. T by cv. This will also be t by cv. Okay, slope are t by cv. Okay, and this is the entropy is remaining constant. Let me write. So S1 is equal to S2, and in 3 to 4 process, S3 is equal to S4. Okay, so I'll write about heat addition and heat rejection here. So heat. Any doubts still so far to anyone? You just have a look on it, how the cycle is looks like. Take about a few seconds, and if you have any doubts, please ask me. Any doubts? Or shall I move forward? Okay. So I'll write a few points about heat addition and heat rejection. Heat addition. So heat addition is basically the internal combustion which is happening. That is, you are providing a combustion when you are spraying the air fuel mixture inside the cylinder and providing a spark. So internal combustion is modeled as a heat addition into the system for from the external source. Okay, that is your spark plug eventually. So the internal combustion is modeled as heat addition into system from external source. Okay. Next, about the heat rejection. Now you're taking heat out. So this is basically your exhaust process, which is in the majority of the gases taken out of the system, okay, out of the cylinder, and it is modeled as a heat rejection. So the exhaust process in which majority of gas is escaped out of the cylinder is escaped out of the cylinder is modeled as heat rejection. Is modeled as heat rejection. Okay. So now one important thing why we are doing, we want some efficiency of a cycle. Basically, what is the efficiency of a cycle, okay, or our petrol engine? That is why we are doing all this. So efficiency is nothing but how much of any system is nothing but how much you took out of the system and how much you provided. Basically it is that. So it is basically the ratio of net work done by the system, net work done by our engine, petrol engine, to that of how much heat you supplied to the system. Okay, that is your heat addition which you are providing through burning the air fuel mixture by converting the chemical energy into mechanical energy. Okay, So efficiency of a system is nothing but efficiency eta is nothing but heat addition, oh sorry, net work to that of net heat supplied, Q supplied. Okay. So what is the network? So network will always be how much heat you supplied minus how much heat was rejected out of the system. So you supplied some heat and you rejected some heat, and the difference of this will give you the network. You supplied some heat and you rejected some heat. So the difference of this will give you the net work. Okay. So I'll write here. This is basically your work net. Heat addition at constant volume minus heat rejection at constant volume. So right here, net work is heat addition at constant volume minus heat rejection at constant volume to that of what is heat supplied. It is heat addition at constant volume. Heat addition at constant volume. Okay. So if you uh, do it like this, it will be what is heat addition? Net heat interaction is nothing but net change in the internal energy of the system. Okay, net heat interaction is net change in the internal energy of the system. So it is basically for a constant volume process. Okay, why I am saying this? In the last tutorial also explained dq from the law of thermodynamics, dq is equal to du plus dw. dw is nothing but pdv. For constant volume process your heat is getting added. Okay, these are heat addition at constant volume, heat rejection at constant volume. When your volume is constant, this is 0. So dq is nothing but cv dt. Okay, so net heat addition or rejection, whatever the interaction is there, it is function of temperature only. Okay, so that is why I'm writing like this. So it will be heat addition cv into addition is happening at, or let us first take the ratio. It will be 1 minus heat rejection at constant volume to that of heat addition at constant volume. So heat is rejecting from which temperature to which temperature? Heat is rejecting from 4 to 1. From 4 to 1. Heat is rejecting from 4 to 1. So heat rejection is cv T4 minus T3. And heat is added from which temperature to which temperature? 3 to 2. 3 to 2. So it is T3 minus T2. CV T3 minus T2. If, as we assume that are in the assumptions that Cp, Cv are all constant for this perfect gas. Okay. So we can cancel out this. So our net heat efficiency will be 1 minus T4 minus T3 to that of T3 minus T2. This is your net efficiency of the system. Net efficiency of the system so far. Okay. So let us box it out. Okay. Net efficiency of the system. Okay. Any doubts still here to anyone? Please ask.
Sir,
Yes, yes. Please ask.
can you scroll back, sir? Can you show the no. Can you show the bar graph?
Yes.
What is mean by HA subscript V?
This one are you saying about?
No. Left side. PV chart.
Yes, in PV chart. Subscript V.
What is mean by HA subscript V?
Heat
HA.
addition at constant volume. And this is
Constant
heat
volume.
rejection
Okay.
volume. Yes, that is what I'm writing. When I will say heat addition
Okay.
at constant pressure in the diesel cycle, then P will come. Yeah. Okay.
Okay, sir. Okay,
Okay.
thank you.
I think it is clear till here.
Yeah,
Okay.
yeah.
Okay. So here we assumed that CV, we are saying that it is a perfect gas and CV is constant. Suppose examiner gives you a question like this. Let us say a question comes like this, that CV is given as function of suppose 0.152 times T, function of temperature. you need to find the efficiency. You need to find the efficiency. How will it be? So in the same formula, okay, what we will do, efficiency is nothing but 1 minus heat rejection to that of heat addition. So heat rejection is Cv dt integration from 1 to 4, because from 4 to 3 or whatever temperature you want, okay, 4 to 3. Heat addition, oh sorry, heat rejection from 4 to 1, T4 minus T1. Why I have written T3? Sorry, my bad. T4 minus T1. T4 minus. I hope everyone is clear that heat rejection was between 4 and 1. Okay. So Cv dt from 1 to 4. And heat addition was happening at Cv dt from 2 to 3. Okay. 2 to 3. So we know that Cv is now not a constant value. It is a function of temperature. So it cannot be taken out of the integration. Okay, it cannot be taken out. So you have to solve with the integration. So 1 minus 0.152 times T dt to that of from 1 to 4, and in denominator also 0.152 times of T dt from 2 to 3. All right, this 0.152 can be taken out and get cancelled out. So this will be 1 minus, what is integration of T dt? It will be T square. T square from 1 to 4, and it will be T square from 2 to 3. So it will be, efficiency will be 1 minus T4 square minus T1 square, and it will be T3 square minus T2 square. Now you need all the temperatures if given by the examiner in the question. Okay. So if this is a simple linear expression, suppose someone gives a quadratic expression. So you have to integrate in that sense. Okay. All right. So this is the efficiency. Efficiency is nothing but 1 minus heat rejection to heat addition. Okay. Any doubts in this? To anyone? Very important things we are doing. So that is why I'm asking. Because I'll start with one good question and then you have to solve, give you some time. Okay, no doubts. Okay, so someone asked in the previous tutorial about the compression ratio. Okay, so now let's come to the compression ratio, because we have to understand first what is this, how the Otto cycle works. So compression ratio, let me write. Let us write a process ratio instead of writing first compression ratio. What is a process ratio for any process? Either it's a compression, expansion, isothermal, adiabatic, whatever the process is. So process ratio. Process ratio. So process ratio is defined specifically, suppose let us say by symbol R. So process ratio is nothing but some ratio of a large value to that of small value. Large to small. Large to small. Okay, so that means eventually your process ratio is always greater than 1 only. The ratio is always going to be greater than. So for any process, it is the ratio of large to small, and it is always greater than 1. Okay, so when we are saying, talking about the IC engines specifically, we say compress, it is a compression ratio in the form of compression ratio. So compression ratio here is R is, what is happening? Compress, from the name suggests compression ratio means compression is happening. We are talking about the compression process, that is from 1 to 2. So which volume is greater, 1 or 2? The volume at point 1 is higher or point 2 is higher? Please tell me. Volume at point 1 is higher or volume at point 2 is higher?
Sir, I think volume at one is higher.
Eventually, 1 will be higher because you have swept the volume from this. This volume is higher on the x-axis, that is volume axis, and V2 is lower. Okay, and from physical sense also, you have swept your pistons from top dead center to bottom dead center where your volume is Vc plus Vs. Okay, whole of the volume has covered. So V1 volume is higher, V2 volume is lower. Okay, so it will be the ratio of V1 by V2. Okay, V1 by V2. Okay, and what is V1? V1 is nothing but Vc, that is your clearance volume plus swept volume. So it will be Vc plus V swept, and volume at point 2 was just the clearance volume. It will be clearance volume. So we can divide by Vc 1 plus Vs by Vc. And we know from the last lecture that Vc by Vs is your clearance ratio. Okay, so that is, it will be 1 plus 1 by C, since C is nothing, that is your clearance ratio, V clearance to that of V swept. Okay, so your compression ratio is defined as 1 plus 1 by C for a Otto cycle. Okay, any doubts? No doubts? Great. So now we will find the efficiency, because we know that efficiency for a standard Otto cycle is 1 minus T4 minus T1 by T3 minus T2. Since efficiency is equal of Otto cycle was 1 minus T4 minus T1 to that of T3 minus T2, T3 minus T2. Now we want to get the ratio value so that we can solve it. Okay, so let us take out T1 outside from it. 1 minus T1 times T4 by T1 minus 1 by, let us take out T2 out of it. From the denominator, it will be T3 by T2 minus 1. Okay, we don't know what are the values of these ratios. Now we want to get the values of these ratios. Okay, so let us see. So it is 1 to 2 is your isentropic compression process. So we can apply the formula for the gas, PV raised to the power of gamma is equal to constant for an isentropic process, right? So we know, since PV raised to the power of gamma is equal to constant, okay, we know that. So from 1 to 2 process, we know that the ratio of T2 by T1 in thermodynamics, we have seen this T2 by T1, and those who have not seen, you can check out my thermodynamic tutorials in my playlist on my YouTube channel. So it will be V1 by V2 to the power of gamma minus 1. Okay, so PV raised to gamma is equal to constant process can be written in this form as well. T2 by T1 is equal to V1 by V2 to the power of gamma minus 1. And we know that V1 is what? V1 by V2. So V1 by V2 is basically your compression ratio only, V1 by V2. We just wrote here, compression ratio is V1 by V2. So it can be written as R to the power of gamma minus 1. Okay, R to the power of gamma minus 1. Okay, R to the power of gamma minus 1. Now for the process 4 to 3, for the process 4 to 3, we know that this is your process, or 3 to 4, whatever you want to say, 3 to 4. 3 to 4 is your isentropic expansion process. 3 to 4 is your isentropic expansion. Again, isentropic formula can be used. I'll write here for isentropic. For isentropic. Okay. So for process 3 to 4, it will be T4 by T3 can be written as V3 by V4 to the power of gamma minus 1. Okay. When we are saying expansion, so then again it will be which volume is higher. If you see from 4 or 3, which volume is higher? Please tell me which volume is higher. Volume 4 or volume 3, which is higher? Yes, Tennyson, right. Volume 4 is higher. Again, it is equal to volume 1 only. 4 and 1 volume are same because it's a constant volume process. 2 and 3 volume are same. Okay. So it will be, just a second, it will be V4 by V3. So it will be 1 by R, because we know that process ratio is always greater than. So V4 is higher than V3. So R will be in the denominator. And when we are seeing an expansion process, we just write a subscript E. When we say compression process, we don't write any subscript with the R. But when we are saying a expansion process, then we have to, or if we are saying isothermal or any other process, we have to write the subscript for that. So that's why you will see E to the power of gamma minus 1. But we have both expansion and because V4 by V3, because since V1 is equal to V4 and V2 is equal to V3. So therefore, this implies V3 by V4 is equal to V2 by V1. Okay, so it can, this implies RE is equal to R. Okay, expansion and compression ratios are same. So we can directly write it as, that means we can write it as 1 by R to the power of gamma minus 1. Now we have the ratios T2 by T1 and T4 by T3. Now we can put these ratios here, T4 by T1, T1 by T2, T3 by T2. We can use all these ratios here. So we know that T4, T1, T3, T2, can this value, bracketed value, just a second, bracketed value can be cancelled out. Is T4 by T1 and T3 by T2 same or not from the graph? T4 by T1 and T3 by T2 is same or not? Tell me. Let us see where I was. See from here. T2 by T1, T4 by T3, T4 by T1 and T3 by T2. Let us rearrange both of them. Okay. Since we know that T2 by T1 is R to the power of gamma minus 1. Since T2 by T1 is R to the power of gamma minus 1 and T4 by T3 is 1 by R to the power of gamma minus 1. And T4, if T4 by T3, 1 by R to the power of gamma minus 1. Can we write like this? T3 by T4 is R to the power of gamma minus 1. 1. Can we write like this? Yes, we have just taken the reverse. So T3 by T4 is equal to T2 by T1. So this implies T2 by T1 is equal to T3 by T4. And what was the ratio? T4 by T1 and T3 by T2. Can we rearrange? Let's take T4 this side. Okay. And other ratio was T3 and T2 and T2 this side. Okay. Let's see. T4 by T1 is equal to T3 by T2. So this ratio is constant. Both are equal. So that is why. Now we can say that this can be used to cancel out. So since efficiency, I'll again write that efficiency was 1 minus T1 by T2. In numerator it was T4 by T1 minus 1, T3 by T2 minus 1. From this, we can say that this and this cancel out. So we are left with 1 minus T1 by T2. And what is T1 by T2? We have T2 by T1 is this. So T1 by T2 is 1 by R to the power of gamma minus 1. 1 by R to the power of gamma minus 1. So it will be 1 by R to the power of gamma minus 1. And this is your final efficiency in terms of compression ratio. That is your air standard efficiency or efficiency of an Otto cycle. Very important. Otto or air standard efficiency. Air standard efficiency. Very important formula. Okay. Efficiency. Any doubts in any of the steps? Please ask me. Although I've written it very clearly, each and every step. So I'll again explain. We know that expansion ratio, sorry, a compression ratio and clearance ratio can be written in this form. Efficiency was 1 minus T4 by T1, T3 by T2. We took out T1 from both numerator and denominator. We got T4 by T1, T3 by T2. Now we want all these ratio values. Okay, so both are isentropic. Sorry, both are isentropic processes. One is isentropic compression, one is isentropic expansion. So 1 to 2 is isentropic compression. T2 by T1 can be written as V1 by V2 to the power of gamma minus 1, and V1 by V2 is nothing but your compression ratio, that is R to the power of gamma minus 1. For the process 3 to 4, it is an isentropic expansion. It will be the ratio T4 by T3 can be written as V3 by V4 to the power of gamma minus 1. And again, V4 is higher than V3. So it can be written as 1 by RE. When we are saying expansion, so we write E in the subscript. So it will be 1 by RE to the power of gamma minus 1. Since we know that V1, V4 and V2, V3 both are equal. So V3 by V4 ratio is equal to V2 by V1 ratio. So we can say that RE and R both are same for our Otto cycle. We put the values, okay, and we get the 1 by R to the power of gamma minus 1 itself. Okay. Now we want this numerator and denominator to be cancelled out. So we saw that T2 by T1 was this, T4 by T3 was this. If we take inverse of it, so T3 by T4 will be R to the power of gamma minus 1. From this and from this, we got the ratio this to be equal. Just transpose the value. T4 by T1 is equal to T3 by T2. This cancels out the ratio of the numerator. We are left with this value. We have already calculated this value. That was 1 by R to the power of gamma minus 1. And this is your final efficiency of an air standard or Otto cycle. Okay, air standard or Otto cycle. Any doubts in this efficiency formula? Please ask me once again, because I'm going to give a numerical after this. Any doubts? Please feel free to ask if any of the step is not clear. It is clear. Okay, attention. Okay, great. If it is clear, then we can go with one question, numerical. Very good numerical. Okay, let me write. For an engine operating on an Otto cycle, clearance ratio of engine is 10%. Clearance volume of engine is 9225 centimeter cube for 6-cylinder engine. You need to find first air standard efficiency, second air bore, stroke, crank radius of engine if engine is over square ratio of 1.75. Okay. Third, heat added in cycle is 1800 kilojoule per kg. You need to find work done. Fourth, maximum temperature of cycle if inlet conditions are if inlet conditions are 1 bar of pressure and 27 degrees Celsius of temperature. Fourth or fifth, temperature at starting of heat rejection. Okay, so you have to zoom it out. Okay, you have to solve this question, and I'll give you a few minutes to solve. You have to actually solve, and I'll ask the answers. Okay. Whosoever gets first, you can also tell me on your own. So I'll give you a few minutes. Take your time, solve this question. It's a very good question, covers all your concept, whatever I have taught so far. Okay, then we will proceed to diesel cycle after this. So I'm here in the class only, but please solve it. And if anything is not clear, you can ask me at any point of time. It's a very easy question. Yes, any doubts? Swararam? Okay. Solve this question. If anyone gets the solution, please tell me. Anyone has solved any of the part? First part, air standard efficiency. Tennyson, have you solved it? Have you got any part? Shanmugam, Shashank, any one of you have got or you have not been able to solve? Viswajit, am I audible to everyone? Efficiency is 61%. Correct. Efficiency is 61.67%. Yeah, just have to apply the formula directly. Correct. Any other part? Ravindran, bore value. What is bore value? Stroke value, crank radius. Heat added in the cycle, maximum temperature. Okay, let us solve. Let us solve then. Let me switch on the camera. Okay, I think I'm visible now. Camera is working. Yeah, okay. All right. So in this question, it is said that for the Otto cycle, clearance ratio is given as 10%. Clearance volume VC is given directly for a six-cylinder engine. You need to find the air standard efficiency first of all. Let us find. Let's come to the solution. So we are given the clearance ratio is 10%, that is 0.1. Okay. We know that clearance ratio is nothing but VC by VS. Okay. So that means your V swept is 10 times of V clearance. Okay. 10 times of V clearance. What is compression ratio in terms of clearance ratio? It is 1 plus 1 by C. Just now we did. So 1 plus 0.1 is nothing but 11. So your compression ratio is 11. Okay. We know the formula for air standard efficiency. We just now solved 1 minus 1 by R to the power of gamma minus 1. So 1 minus 11 to the power of gamma for air is how much? 0.4. 1.4 minus 1. So that will be 0.4. So it will come out to be 61.67 in percentage. So efficiency you got as 61.67%. Okay, very easy. Next question. What was next question? You need to find the bore, that is the diameter of the cylinder. We have introduced this terminology in the previous tutorial. The stroke, that is your length L, crank radius small radius R of the crank rod, and if the over square ratio, that is L by D ratio, is given as 1.75. So Second part, we are given the L by D ratio is 1.75. We are also given the clearance volume as 9225 for 6 cylinders, okay, in centimeter cube. 9225 for 6 cylinders. So for one cylinder, it will be by 6, that is 1537.5 centimeter cube for each cylinder. For each cylinder. Okay, you got the clearance volume. Okay, we know that swept volume is 10 times of clearance volume. From here, we just know that because clearance ratio is given to us. So V swept is 10 times of VC. We know that VC is nothing but you put here 10 times of 1537.5. So this will be your swept volume. We know that swept volume is nothing but pi by 4 d square into L. So it will be pi by 4 d square into L is nothing but how much? You are given 10 times 1537.5. You know that L by D is 1.75. So you can write L as 1.75 of D. Okay. Put this L here. So this will be pi by 4 d square into 1.75 of d is equal to 10 into 1537.5. So from here, your d will come out to be 22.36 centimeter. If you got d, so therefore your L will also come out to be 1.75 times d. Put this d here, that will 39.142 centimeter. So you got the length as well as bore of the stroke as well as bore of the cylinder. Okay, of the cylinder. Then it was asked crank radius. We also know that since length of the stroke is nothing but 2 times of a crank radius in one revolution. In one swept, one length is covered and it is equal to from top dead center to bottom dead center, it is 2r, small r. Okay, so L is 2r. So from here, r will come out to be L by 2. Put this L here. So this implies your R will come out to be 19.57 centimeter. So second part is also over here. Okay. So we found out what is diameter, what is length, and what is crank radius. All these three values we got. Here we got the efficiency as well. Efficiency. Okay. From the first. Now third part, what is third part? Heat added in cycle is given. Heat addition at constant volume is given to you 1800 kilojoule per kg. Find the work done. Okay, very good part. So third part. So heat added. So you got the efficiency that is 61.67%. So that is 0.6167 in terms of ratio. Efficiency is nothing but net work done to that of heat addition at constant volume. You are given heat addition directly. So work done will be, heat addition is how much? 1800 is equal to 0.6167. So from here, work done will come out to be how much? It will be 689.2 kilojoules. Sorry, not 689. It will be 1110.06 kilojoule per kg. This is your work done, which was asked. Okay, work done. So next part was find the work done. Next part is maximum. Fourth part is maximum temperature of cycle if inlet condition is 1 bar and 27 degrees Celsius. Let us find out first heat rejection also. So what will be heat rejection? Fourth point. We know that net work done is heat addition at constant volume minus heat rejection at constant volume. Work done you got 1110.06. Heat addition was 1800 and heat rejection at constant volume. So heat rejection will come out to be 689.2 kilojoule per kg. You got the heat rejection. And what is the expression for heat rejection? It is CV times from 4 to 1 process the heat rejection happens. So CV times T4 minus T1 is 689.2 689.2. CV, you know, for an air is how much? 0.718. Okay, standard value. And T4 you don't know, but T1 you know. Okay, what is T1 given to you? The T1 is given to you as 27 degrees Celsius. Okay, 27 degrees Celsius. So let us put in Kelvin. How much? 273 plus 27 is 300 Kelvin. All units in SI. Okay, is 689.2. So T4 will be 1259.8. 9.8 Kelvin. You got the T4 value. Okay. But what they have asked maximum temperature of the cycle. Maximum temperature of the cycle is not T4. It is, if you go to the cycle, let me show to the cycle. Maximum temperature of the cycle is T3. You still don't know. You know what is T1. You know what is T4. You don't know T2 and T3 so far. Okay. Let us find out. So we know that T2 by T1, we have got this expression as V1 by V2 to the power of gamma minus 1. And V1 by V2 is nothing but compression ratio, is your R to the power of gamma minus 1. So if you put T2 you don't know, T1 you know from the question, that is 300 Kelvin, and R was 11 to the power of 1.4 minus 1. So from here, your T2 will come out to be 782.8 Kelvin. Now you have T1, you have T2, you have T4. You don't know still what is T3. Okay, so T3 will come out from the heat addition process. So since heat addition at constant volume is nothing but CV T3 minus T2. Now you know what is T2. Okay, and you also know heat addition value because you calculated here. Oh, sorry, it is given to you. That is 1800 kilojoule per kg. Okay, so it will be 1800 equal to 0.718. T3 you don't know. T2 you just calculated here. That is 782.8. So from here you will get your T3 value as 3289.8 Kelvin. Okay, so you can imagine that the temperature is very high and it is the maximum value of the temperature. So you got the temperature value also. What was the last part? The last part was temperature at starting of the heat rejection. We have already calculated that. Temperature at starting of the heat rejection is nothing but T. Heat rejection happens from which place to which place? So heat rejection happens, if you see in the cycle, from 4 to 1. We have already got T4 as well. T4 as well. Yes, correct. Okay. So what was T4? We have already calculated this. So this was your fifth point as well. And this was your fourth point. Is it clear? Was it a good question? Every concept is covered in this, whatever I have taught so far. Okay. Each and every concept. All right. I hope there is no doubt. If you have any doubts, please ask. Otherwise, we will start to the diesel cycle. Move ahead to diesel cycle. No doubts? Shall we move forward? Okay. Can anyone confirm me that every one of you were able to access the lecture, this tutorial video and the notes which I provided? Were you able to access? Or anyone you have a doubt of that? Were you able to access the lecture videos? I hope NPTEL team might have mailed you about that scenario. Okay. All right. Okay. Next is diesel engine. Petrol engine we are covered. Diesel engine. Okay. So what is difference between diesel engine and petrol engine? First of all, in shape, you will see that diesel engine will be a bit bigger in size compared to a petrol engine. Okay. In a petrol engine, you during the suction stroke, air fuel mixture is injected. Okay. during the suction stroke. But here during in diesel engine, the during the suction stroke only air is injected during suction. Okay, the fuel is injected during the compression stroke, and there is no spark plug in the diesel engine. Okay, there is no spark plug in the diesel engine. Why? Because when the compression stroke happens, at that instant, the fuel is started to get insert inside the cylinder, and air and fuel get mixed, and due to the compression, that pressure and temperature rises, and the temperature is self-sufficient so that it is greater than the ignition temperature of the cylinder. That is why we don't need a spark plug for the uh, diesel engine to ignite the diesel fuel. Okay, the stroke is quite very high compared to a petrol engine. This is the only difference which happens, and here when the heat is getting added, it is adding at a constant pressure, not at constant volume. I'll explain, write down every step here, don't worry. Okay, let me write it down, then you will understand. So only air is entered into cylinder during suction stroke. Due to high compression ratio, temperature inside cylinder after compression becomes more than the self ignition temperature. Okay, hence as the fuel enters into the cylinder, it starts its ignition, and during that time period, piston displaces and it is measured as heat addition at constant pressure. That is heat addition at constant pressure. Okay, now one of you asked that subscript, this was the point at that time. When you are writing heat addition at constant volume, you write V in the subscript, but for constant pressure you write P in the subscript. Okay, so in the schematic diagram, if I make of a diesel engine, how different it will look like. Okay, so the diesel engine will look like this. So I'm making the diesel engine, again the cylinder. Okay, these are your inlet valve during suction. Okay, exhaust valve is closed. This is your not your what we say spark plug. This is your fuel injector. Okay, fuel injector. Okay, this is your from where diesel is injected. Okay, again you have a piston. Okay, suppose this is your TDC, this is your PDC. I should not till the end, I should make PDC. Again, this is your connecting rod. This is your crank rod, and this is connected to a shaft eventually and a flywheel. So this time, if I say this is your flywheel, and let us say this is your radius of your in which your crank is revolving. Okay, this is your flywheel. Okay, and this is your crankshaft. This is your connecting rod, and this is your crank rod. Okay, and these are your inlet and exhaust valve, IV, EV. Okay, all right. Because it has a new component, and the fuel injector is quite a heavy component when you see. So eventually vibration and noises are going to increase. And if vibration noises are high, this whole setup is also very huge compared to a petrol engine. If I make a comparison that how a petrol engine will look like, so petrol engine will be one cylinder of a petrol engine will be, suppose in scenario like, I'm just giving an estimate. So it will look something like this. Flywheel, suppose here. So flywheel is also smaller. Cylinder sizes are also smaller. Okay. So this is a petrol engine. So this hole is your diesel engine, and this is your petrol engine. Okay. Now you can actually feel the sense that how different. If you see the trucks, the heavy loading vehicles are very. If you see a cylinder of a truck, or if you see a cylinder of a train, okay, the diesel engines, very huge sizes. Okay, so here vibration and noises are high comparatively. Let me write. Let me use some another pen. Yes, any doubts? Anyone of you have unmuted? Vibration and noises. If you see a diesel engine have a high vibration and a high noise compared to a petrol engine. In petrol engine, yes, any doubts? Someone has unmuted. A vibration and noise is less. Yes, Sai Kumar, any doubts? You have unmuted. No doubts. Okay. Please keep yourself muted if no doubts are there. Okay. So in petrol engine, these are noises are down. If you see, the power of any system is defined for a mechanical system is defined as power is nothing but torque into angular speed, that is omega. Okay, torque into omega, torque into omega, torque. So diesel engine for a diesel engine, the torque is very high and speed is less. That's why you don't see trucks racing at 200 kilometers per hour. Okay, but they provide a very high torque. Power is same. Both engines, either it's a petrol engine or a diesel engine, both will produce same power. Suppose they are of same power, but the torque produced in a diesel engine will be higher compared to a torque produced by a petrol engine. Whereas the angular speed, the speed of the engine provided by a petrol engine will be higher compared to a diesel engine. Okay, but the power remains same. If the power is same, okay. If I say if a power is same, then torque will be less and omega will be high for petrol. Whereas torque will be high and omega will be less for diesel engine. Okay, for the same power output. Okay. Any doubts? And the compression ratio, if you see, the stroke length is quite high in a diesel engine. That's why when the compression is done in the diesel engine, it provides, why is it like that? Uh, why is it like that? I don't understand why is it like that? You are saying tension. You can unmute yourself and tell me. So if I'm saying,
Hello.
yeah,
Is
yes,
it audible? Okay.
I can.
Why this the torque, this compression ignition, that is the diesel engine is higher for the same power compared to petrol engine? Why it's happening?
Compression compression ratio is higher. That is
No, no,
you are
no.
asking.
The torque of the diesel engine is higher that compared to petrol engine for the same power output.
That
So
is what I'm saying. That
why
is what
why it's like that?
power is nothing but torque into omega. What is torque? L cross R basically. Okay, R cross L or L cross R. The length and the radius. If you see the crank radius of this and this, which one is higher? Of a diesel engine or of a petrol engine?
So it's for diesel engine.
Diesel engine. So that means torque is higher mathematically if you see. And eventually for same power output, the diesel engines are able to carry more load. That's why the assembly of the engine assembly is quite very heavy and big. If you see, it's a cast iron diesel engine. If you say in the trucks if you are using, they are very heavily loaded in tractors, trucks, or even in the cars also. Diesel engine car will be a very higher when compared to a petrol engine car. Okay, if I'm just talking about the diesel engines, not the whole assembly of the car. Okay, so like one manufacturer can use two cars, one of diesel and one of petrol variant. One can of the same model, suppose, but one can reduce the like metal body or some another parts can be made of a different scenarios for a diesel and for a petrol engine. I'm not talking about the whole assembly, but only the engine assembly. Your diesel engine assembly will be much heavier compared to a petrol engine assembly, as well as the swept volume. If you see, if we talk in the trucks, if you say heavily loaded trucks, the swept volume is quite very high. And when the swept volume is quite high, the pressure and temperature which is achieved during the sweep from bottom dead center to a top dead center is enough so that the temperature achieved is comparatively higher than the self ignition temperature of the diesel. Okay, any doubts now? Is it clear? So in Otto cycle, the compression ratio, that is large volume to a small volume, is quite lower, because if you see the volumes is the total volume swept is very less compared to a total volume swept in the diesel engine, if you see in the size comparison. Okay, so eventually the Otto cycle will have a less compression ratio, swept volume will be less, whereas a diesel engine will have a higher compression ratio. And there are standard values as well. If I say, I put a note here, let me write a note. Compression ratio of Otto cycle is generally between 6 to 12. Okay, so because of that, your temperature when you are compressing the air fuel mixture, the temperature is not that sufficient. That's why you need an external spark from the spark plug. Okay, so compression ratio is there, whereas for R of diesel cycle is from 16 to 22. Okay, 16 to 22. And T self ignition here, T2 by T1 is your ratio. So T self ignition will be greater than the T2 because your compression ratio is high. T2 by T1 is nothing but your R by gamma minus 1. If your T2 is high, your self ignition uh, doesn't require. So self ignition sorry, not higher, self-ignition will be lower compared to the T2. Okay, so the fuel can burn itself without any spark provided. So we can say that self-ignition temperature of petrol is much greater than self-ignition temperature of diesel. Okay, that's why you need an external spark plug for this. So I'll write here for diesel engine, heavy compression ratio always towards 22 or more, whereas for petrol engine always towards 6 or less than 6. Okay, all right. So that's why you see now that your high sports cars cannot be a carrier, like person carrying lot of persons they cannot carry, whereas your truck can carry lot of load compared to high speed. Okay, so now let's make the diesel cycle. Okay, we have understood how the diesel engine works. Diesel cycle, or we can say that constant pressure heat addition, P is equal to constant okay. So more or less it will be similar to the Otto cycle only, instead of the process of constant pressure heat addition up instead of constant volume heat addition from Otto cycle. Okay, so if we say this is again my PV plot. So first process is your again isentropic compression from 1 to 2. Okay, isentropic compression, then 2 to 3. Let me again make this bigger. 1 to 2 constant isentropic compression. Okay, that is your PV to the power of gamma is equal to constant. 2 to 3 is your constant pressure heat addition. So constant pressure heat addition means at constant pressure horizontal line will come and heat is added at constant pressure. So heat added at constant pressure, not at constant volume this time. Okay, next is your power stroke, that is your expansion stroke. Again it's an isentropic expansion, isentropic expansion 3 to 4. So isentropic expansion that is PV raised per gamma is equal to constant. Okay, and final will be heat rejection will happen at constant volume. Only the difference is of heat addition at constant pressure is the difference from the Otto cycle. Heat rejection at constant volume. So heat is rejected because at exhaust at that instant 90% of the gases escape out. Okay, and then again we can say that the area under this graph is your work net. Okay, area under the graph is your net work done by the cycle. Net work done by the cycle. Okay, similarly we'll plot the temperature entropy plot as well. Temperature entropy, that will look more or less same with one difference now. So 1 to 2 is again your isentropic compression process. So at constant entropy, temperature is rising. So at constant entropy from 1 to 2, temperature is rising. Okay, entropy is remaining constant here. Okay, from 2 to 3 is your heat addition at constant pressure. So some slope will be there again here. So let us say this is your heat addition at constant pressure. Then 3 to 4 is your isentropic expansion. Again at constant entropy, temperature is decreasing. Okay, because you are doing an expansion. 4. Okay, and then final is heat rejection at constant volume. When you are taking out the heat, again temperature will drop further. Okay, so 4 to 1 is your isentropic, sorry, heat rejection at constant volume. Now if you see, the slopes are not same here. Suppose this is theta 1 and this is theta 2. By visualization also I've made that theta 2 is looking much greater than theta 1, and there is a science behind it. What is the science? Is that we know that dq is equal to TdS. Okay, and dq is equal to Cp dt. If I say about process 2 to 3, that is your heat addition at constant pressure. So it will be Cp dt is equal to TdS. So slope is dt by ds. It is T by Cp. Whereas process 4 to 1, dt by ds is T by Cv. And since we know that value is Cp is greater than Cv for a air, okay, and Cp is generally greater than Cv. So you can sense that this will be higher than this. So your slope, this whole ratio will be less than the other ratio. So slope of a constant pressure process will be lesser than the constant volume process. Constant pressure, constant volume. So this implies dt by ds of pressure is less than dt by ds of constant volume. So you can see that theta 1 is less than theta 2. This implies that theta 1 is less than theta 2. Is it clear? Or any doubts? That's why I made this like this. Don't make parallel lines in this. Examiner will cross that. Any doubts in this? Please ask if you have any doubts. Now we will derive the efficiency also. But before that, let us understand the heat addition at constant pressure process in much detail now. Okay, what is actually happening in the diesel engine at that point of time? Let us understand. So let me again make the cylinder. This is your fuel injector. Okay, P in the injector is higher than the cylinder, and it is very high. Okay, much greater than P in the cylinder, and P in the cylinder is greater than again P atmosphere. Okay, and suppose this is your TDC. Okay, TDC. Okay, so P in the cylinder is greater than the P atmosphere at below side. Or sorry, not this side. This is after the compression has happened. This is the stroke I'm talking about, that stroke. Okay, so cylinder pressure will eventually increase. Okay, because you are going to get the exhaust, you are going to get the power stroke out of it. So what is happening actually? Now let us bifurcate this much more. So if I'm saying that pressure in cylinder is higher than the atmosphere, so that means temperature will also be higher than that atmosphere in the cylinder, because you are going to burn your fuel. Why I am saying that? Your burning will happen, or heat is adding at a constant pressure. Let me make it once again. Let us suppose this step was point number 2, and let us suppose a piston has also moved down. Suppose still here, somewhere here. Okay, so from point 1 to point 2 to point 3, piston has moved. Okay, and fuel, what is the fuel injector doing at from this position to this position is that as soon as at point 2 the maximum compression has happened, the system says that from the electronic circuit, the sensor says that now start spraying the fuel inside the system. So when the fuel is getting inside the, you can say, the piston cylinder arrangement, when the fuel is injected, that is your diesel is getting injected in your cylinder. At that time, piston is not stopping. Sparking in the petrol engine, sparking was at an instant. That is why you are saying that at constant volume, if your piston would have been at top dead center itself, at that instant itself, the spark was given. And sparking was very, very fast. That's why the heat was added at a constant volume, because there was fuel already, air fuel mixture was already inside the cylinder. But here you are supplying the fuel. And when you are supplying the fuel, your injector pressure is constant. So suppose your injector pressure here, if I'm saying that injector pressure is higher than the cylinder or atmospheric pressure, so suppose I'm saying 10 bar of injector pressure. I'm just taking an example. 10 bar of injector pressure I'm providing. So the fuel is injecting at a constant 10 bar of the pressure. But in the meanwhile, piston is not at the same position too. Piston is also moving. It's a very fast process, but piston is also moving. So piston is moving from point 2 to point 3 by spraying the, similarly, the spray is also of the fuel, diesel is also coming here. Spray of the diesel is also coming here. Okay. So that is why the fuel injector is providing the at a constant pressure. The diesel is provided at a constant pressure. And meanwhile, the piston is also moving. It is not a heat addition at a constant volume. It is a heat addition at a constant pressure, because the fuel is injected inside the uh, cylinder from the fuel injector at a constant pressure. That is your injector pressure. And fuel is getting added from position 2 to position 3. It is not that till bottom dead center it will go, the piston will move and fuel will be getting till the bottom dead center. No, bottom dead center is somewhere here. But fuel will be injected for some amount of time. We don't have unlimited amount of fuel, and we cannot burn unlimited amount of fuel as well. So we say that from point 2 to point 3, our fuel is getting injected. And eventually, if I'm injecting a fuel, there will be some cutoff strength also. Like till from which position to which position, I'm saying that my fuel is getting injected. Okay. And when the fuel is getting injected, so the self ignition, that is basically the temperature will be rise higher than the self ignition, not at point 2, it will be at point 3. Till point, from point 2 to point 3, fuel is injecting. As the point 3 is achieved, the temperature inside the cylinder has reached the self ignition temperature of the diesel. And now immediately the diesel burn. And it is not like very high value. It is very, like, if point 2 is here, the point 3 will be just here. I've just made a very high value just to showcase you all. Okay. But in actuality, it is not so much gap. Okay. So that is why at point 3, so this is the volume which is VF, which has been covered, for which the fuel was injected. And at point 3, it's almost greater than T of self ignition. Okay. And here, point 2, the fuel started burning. So self ignition was almost equal to T of cylinder, what was during the compression has happened. Okay. Is it clear, or any doubts in understanding the science behind it? What is actually happening? What is the mechanism happening from during the fuel injection process? Because I will come up with that some terminologies here. Any doubts, please ask. If no doubts, then we can proceed. So we know that we are supplying the fuel for certain amount of time. So that means we are going to stop the fuel when the power stroke is happening. Okay. So we can say that rho is nothing but your cutoff ratio. And again, if it's a ratio, process ratio, higher by lower. So from V3, will be greater than V2. Okay, V3 by V2, because fuel injected will be higher in third point compared to 2. Okay, V3 by V2. We know that compression ratio is V1 by V2. Okay, compression ratio is V1 by V2, and expansion ratio was from which point to which point expansion is happening? Expansion is happening from 3 to 4. So V4 by V3. Higher by lower, V4 by V3. Suppose if I divide by V2 in numerator and denominator here, V4 by V2 to that of V3 by V2. So we know that V3 by V2 is cutoff ratio. And V4 by V2, V2 and V2 and V4 and V1, sorry. V4 and V1 are equal. So this can also be written as V1 by V2 to that of rho. And V1 by V2 is nothing but your compression ratio from here. So your R expansion ratio will be R by rho. So that is where two new terminologies also included, expansion ratio and cutoff ratio. Whereas we saw that in our Otto cycle, expansion ratio and cutoff compression ratio were same. There was no cutoff ratio defined because it was fuel was supplied already during the suction stroke. But here you are providing a fuel for certain amount of time. Okay, so that is why it is a RE by R expansion rate. This is your expansion ratio. Expansion ratio RE. Any doubts in understanding this? No doubts? Okay. Let's write a note here. So if I'm saying that fuel supplied is percentage of swept volume, Vs. If you are supplying fuel for some percentage of the complete swept volume, that means fuel is supplied from V3 to V2. So V3 minus V2 is percentage of swept is happening from 1 to 2. Okay, V1 minus V2. Okay, if I divide by V2 both sides, so it will be V3 by V2 minus 1 is some percentage of V1 by V2 minus 1. That means V3 by V2 is your cutoff ratio. Rho minus 1 is percentage of V1 by V2 is your compression ratio, R minus 1. Okay. If some statement comes like this, that means rho minus 1 is percentage of R minus 1. If I'm saying, suppose for an example, if I say cutoff at 10 percentage of stroke, that means my volume at position 3 when the cutoff has completed will be 0.1 10%. So 0.1 time of swept volume plus clearance volume will also be there. Okay. And what is swept volume? V1 minus V2. And what is clearance volume? V2. If you see from the graph, the clearance volume is V2 and the is V3. If you divide again, V3 by V2 is equal to 0.1 times V1 minus V2. Oh, sorry, V1 by V2 minus 1 plus 1. So V3 by V2 is again rho minus 1 is 0.1 times of R minus 1. Again, same. If you see from both sides. Okay. That is also same. Now let's come with the efficiency. Again, efficiency is nothing but net work to that of heat supplied, and this time heat is supplied at constant pressure, not constant volume. So net work is heat addition at constant pressure minus heat rejection at constant volume to that of heat addition at constant pressure. Okay, so we can write it like this: 1 minus heat rejection at constant volume to that of heat addition at constant pressure. Okay, What is heat rejection? Heat rejection is happening at constant volume, C4 times T4 minus T1. Whereas heat rejection is Cp this time, not Cv. It is a constant pressure process. It is T3 minus T2. T3 minus T2. Okay, T3 minus. Don't misjudge this 2-3 notation. Don't misjudge this 2-3 notation with sorry, always take, my bad. Don't say that these two are separate. This 2-3 and this 2-3 is same only. Okay. 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 So where were we? So heat is added at a constant. So what is basically, let me write here one point also. To green point. So this is basically from 2 to 3, you are providing the fuel and heat is getting added. So this is fuel supply from 2 to 3. And point number 3 is basically your cutoff point. Cutoff. Okay, cutoff. Yes, so we were at efficiency. Yeah, efficiency. So again, C4 times T4 minus T1. So we know that Cp by Cv, since we know that Cp by Cv is your gamma, is the ratio. So it will be 1 minus 1 by gamma T4 minus T1 by T3 minus T2. Now let's get all the ratios once again. So we know that this is your so far efficiency. We want all the ratios. Since we know that T2 by T1 is compression ratio to the power of gamma minus 1. We have already done multiple times. So this implies your T2 will be T1 times R to the power of gamma minus 1. Okay. Then we know that T3 by T2. This is heat addition at constant pressure. From 2 to 3, heat is adding. This will be equal to V3 by V2. This is not an isentropic process that you will put some value. Okay, V3 by V2. So this implies what will be V3 and V2. Let us see. Since we know that expansion ratio is V4 by V3, higher to lower. If you see, expansion is happening from 4 to 3, 3 to 4. So expansion is happening from 3 to 4. So V4 is higher than V3. So it will be V4 by V3 expansion ratio. And V4 and V1 are equal, and V3 and V2 are not equal. So it will be V3 only. Okay, V1 by V3. And we also know that expansion ratio is compression ratio to that of gamma. We have just proved this here. Expansion ratio is R by gamma. R by rho, sorry, why I'm saying gamma, R by rho. Okay, so from here, what is rho? Since rho is cutoff ratio V3 by V2 and R is V1 by V2. Okay, you can put the values. So you will get finally T3 by T2. Your V3 value is rho times, sorry, what I'm doing wrong, anything wrong. Sorry. So T2 will rho times V3. Okay. So T3 is V3 is how much? Rho times V2. And you know that T2 is nothing but your T1 into the power of R to the power of gamma minus 1. So, and T3 is rho into V2 and T2. Rho into V2 and T2 is T1 into R to the power of gamma minus 1 from here. Okay. All right. Any doubts? Anyone has any doubts still here? Am I doing something wrong? Oh, sorry. This V2 was also there in denominator. That is what I was thinking, by V2. So this V2 and V2 cancels out. Rho into T1 R to the power of gamma minus 1 is your T3. And finally, during the isentropic expansion, since you know that T4 by T3 is V3 by V4 to the power of gamma minus 1. So you can write T4 as V3 by V4 is nothing but your V3 by V4 is your expansion ratio, right? Or am I wrong? Expansion ratio, yeah. An expansion ratio can be written as R by rho. So can I write it as T3 times R by rho to the power of gamma minus 1. Clear? And if I put this T3 here, your T4 will come out to be T1 into rho to the power of gamma. So now every variable, T4 is in terms of T1, T3 is in terms of T1, and T2 is also in terms of T1. Now you can put all these values in the efficiency. All these values in the efficiency. Okay. Since efficiency was 1 minus 1 by gamma T4 minus T1 to that of T3 minus T2. Put all the values 1 by minus 1 by gamma. T4 is rho to the power of gamma times T1 minus T1. T3 is rho to the power of R in rho into R to the power of gamma minus 1 minus into T1 minus what is T2? It is R to the power of gamma minus 1 times T1. So now every value is in terms of T1. So T1, 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 T1 cancels out. So your final value is 1 minus 1 by gamma rho to the power of gamma minus 1. And from here, if I take out gamma, sorry, if I take out R to the power of gamma minus 1 outside, I'm left with rho minus 1. Okay. The final formula is efficiency of diesel, or you can say air standard diesel cycle is 1 minus 1 by R to the power of gamma minus 1 after rearranging rho to the power of gamma minus 1 into gamma into rho minus 1. Very important expression. Air standard efficiency of a diesel cycle is this. Air standard efficiency of a diesel cycle is this. Is it clear or any doubts? This is our air standard efficiency. You will again go through these notes now, so you will understand each and every step. I have written it very clearly. Any doubts? Clear. Great. It's clear. So I think we can end the session here itself. If you don't have any doubts, we will end the session. So you all will get this lecture notes by the NPTEL team. A sheet comes where the link of this session which is getting recorded, and I'll also upload the lecture on my YouTube channel. The name of my YouTube channel is, again I'll write, those who have missed, the name of my YouTube channel is NPTEL space with space Varnit. My name is Varnit Kapoor. Okay, this is my YouTube channel. All the lecture recordings I put, these tutorial recordings I put on this channel. In the video description of each video, there is a drive link where you will see the PDF of all these notes, which will be available. Okay, and also the NPTEL team will also mail you the lecture recordings and the PDF links. Okay, don't worry about that. That will evidently redirect to my channel only. Okay, that's why I'm writing here. If people don't want to wait from the NPTEL team side. Okay. So let us end the session. If there is no doubt, I'll see you next week, next Tuesday, same time, 6 to 8 p.m. Okay. Thank you.